My name is Juana Moreno and CCT and Physics Department. We are really lucky to have this funding because this allows us to collaborate with the best people in Germany and Switzerland in our field. Our student goes there to visit our collaborators, and the students of our collaborators come here to work in our group. I think so far has been pretty successful. We have also courses teach using video conferencing. We have a class from ETH Sweden last year. We are going to have another one this year in different locations. Other universities are also involved, and I mean, I think that it's really a great project to be working on. The first call for proposal was, I believe, 4 years ago, and the second one was the one we win. This stamp for Partnership for International Research and Education. The point is NSF wants to get more international collaboration between the US and other regions. So the Office of International Science and Education put this as a big, I mean, they really want to move that program forward to get more international projects. This grant, we won it when Mark Jarrell was at the University of Cincinnati and I was at the University of North Dakota. So for 1 year, we used video conferencing to keep our group meetings, all that. But then we have the opportunity of coming here, and we really thought that will ease the project, the coordination of the project, and that's the reason now all our students and postdocs that are funded by this hour are here with us. This, I think, is a great project for a student because, I mean, they have the best of, I mean, they have 2 advisors they can learn from. They are able to travel international. They are able to participate in courses and compare themselves with the students in the best research and institutes in Germany and the best universities there. And I think that's for the student, I mean, it's very good.
There's something called a semiconductor roadmap. And the semiconductor roadmap predicts what's going to happen to the materials, which is going to make faster and faster CPUs and better electronics. Well, that roadmap has a road closed sign on it, just about a decade away, where you can no longer scale the present technology to go beyond that point. And when that happens, we're going to have to introduce new technology, such as spintronic technology, or maybe multi-layers of these transition metal oxides, which constitute the cuprates, or something else maybe we haven't anticipated yet to develop the next generation of electronic devices. But one thing is for sure, those electronic devices are going to be correlated quantum systems. They're not going to be these classical semiconducting systems. So what we're doing really is really cool. We're doing the basic theory, which we hope 20 years from now is what's going to be in your wristwatch or your television set or your, I don't know, embedded into your brain or something. The complex phenomena which we observe is related to strong correlations between electrons, which cause the moments to form, and then those moments to become correlated and so on. And I think everybody in the condensed matter group here is working on correlated systems, either on the experimental side or the theoretical side. The only real exception is Dan Sheehy, and he's working in atomic traps, where the analog is very strong. Well, I think the essential thing is it's both physics and computation. We're dealing with systems which are complex. I mean, look at all the lines up here, and that doesn't even do it justice. To treat complexity, you can't really just use a reductionist theory. Reductionist theory, almost at this point, you're putting in the answer and then doing a lot of calculations and saying, aha, look at what we got. Well, we don't want to do that. We want to see the complexity emerge from sort of a top-down level where we have the basic Hamiltonian. We use computational tools to solve that Hamiltonian, and we see the physics emerge at the bottom end. You know, there's traditionally there are two ways of doing science. There's theory and experiment, and almost all of the national societies for chemistry and physics and biology now acknowledges that there's a third co-equal method of scientific inquiry called computational science. And LSU is one of the few places in the world where computational science is broadly based. I'm sorry, I shouldn't even use that word science. It's computational technology here. That is, at the CCT, where Juana and I have joint appointments, half-time appointments, computational technology is used to not only explore the properties of materials, but also, you know, astrophysics and biophysics and chemistry. But it goes beyond that. I mean, there's some of the coolest talks are computational music, right, or animation, right? In fact, we have a famous animation festival associated with the center. And in fact, our director is actually a computational musician, the director of our CCT. So what's really cool about what LSU is doing is that they're taking this third method of inquiry and applying it throughout the areas in the campus. Business, for example, is another area that I forgot to mention. So that's really unique, and it's really neat, and it puts us at the forefront. I mean, I think eventually all other universities are going to have to do this because computation is the third method of inquiry, but LSU is sort of at the forefront of that, which is very nice. We have different funding sources. One is a SIDAC, which is a large program spread across multiple universities for scientific discovery through advanced computation. We have individual, one has a career grant, and I have an individual investigator grant from NSF. We're also part of two computational material science networks, which are Department of Energy, Basic Energy Sciences networks to try to get synergism between different computational scientists so that the tricks learned here will quickly migrate to other locations.